Hi all, welcome back to another session of Ball Computer. In this session, I am continuing the topic chemical kinetics. So in last session, we have dealt with the order and molecularity of the chemical reactions. Then we are dealing with the topic that is elementary and complex reactions. So according to collision theory, we found that the reactant molecules continuously collide each other and resulting in the formations of a product in a chemical reactions. And we found that the number of reactive chemical species, that can be molecules, that can be atom or ions, which collide simultaneously and bring about the chemical reactions are termed as the molecularity. So if these molecules in the reactant part continuously collide each other and result in the formations of a product in one step is termed as the elementary reactions. So consider this example, that is the decompositions of ammonium nitrite to give nitrogen and water. Here the molecularity is 1 because there is only one molecule of ammonium nitrate which undergo decompositions to give nitrogen gas and water. So here it is a unimolecular reactions, and in these reactions when we look the reaction, here these reacting molecules continuously collide each other and result in the formations of these two products in one step. So this is an example of an elementary reactions. Similarly, consider the decompositions of hydrogen iodide to give hydrogen molecule and iodine. Here the molecularity is found to be 2 because there are two molecules of Hi and this is giving to H2 and I2. So when we look this reaction also, here the two molecule of Hi is continuously colliding and resulting in the formations of H2 and I2 in single step. So this is also an example of an elementary reactions. So suppose if there are more than 4 reactant molecules in a chemical reactions, then these reactant molecules cannot collide simultaneously each other in one step. That means the product formation cannot be occur in one step. So such reactions in which the reactant molecule collide simultaneously and result in the formations of a product in number of steps is termed as the complex reactions. So consider this reaction, that is 2MnO4 negative plus 5C2O4 2 negative plus 16S plus giving 2Mn2 plus 10CO2 plus 8H2O. When we look the molecularity of these reactions, we found that here there are 23 reactive species are there. And we can surely tell that these 23 reactant molecules cannot collide each other simultaneously in one step. That means the product is formed in number of steps. So this is an example of a complex reaction. So we know that a detailed descriptions of various steps involved in the conversions of reactant to product is termed as the mechanism. And again, when we look the mechanism, some step in the mechanism will be very fast. Some step in the mechanism will be very slow. That means each step in the mechanism do not take place at the same speed. So while writing the mechanism of the reaction, the step which are taking place very slowly is termed as the rate determining step. That means the overall rate of the reaction depending upon that slowest step, and it is termed as the rate determining step of that reaction. So consider the catalytic decompositions of H2O2 by I negative in alkaline medium. And when we look the rate law equation experimentally, it is found to be R is equal to K into concentration of H2O2 into concentration of I negative. That is, reaction is first order with respect to H2O2 and with respect to I negative. But overall order of the reaction is found to be second order. But with respect to H2O2, the order of the reaction is first order. And again with respect to I negative means it is again the reaction is found to be first order. That means this reaction is taking place in two steps. And when we look the mechanism of that reactions, it is found that is H2O2 on reacting with I negative, it gives H2O and IO negative, and that is a slow step. And second step involve a fast reaction, that is the reaction between H2O2 and this formed IO negative, and it results in the formations of water and I negative and O2. So when we look the rate law, it is found that it is depending upon the concentration of H2O2 and I negative. And when we look the mechanism, there is a formations of an intermediate that is IO negative. It is not involved in the rate of reactions. So because when the overall balancing the chemical reactions, this is not involved. So the rate, this lowest step is the rate determining step, and that means rate is depending upon the concentration of H2O2 and concentration of I negative. So we have found that elementary reactions means are those reactions in which reactant molecules collide simultaneously and result in the formations of the product in one step means it is termed as the elementary reactions. And if the reactant molecules collide simultaneously and result in the formations of the product in number of steps is termed as the complex reactions. And again, while discussing the complex reactions, we have to understand the mechanism of the reactions, and because the overall rate of that reactions depend upon the slowest step in the mechanism, and that slowest step is termed as a rate determining step in a complex reaction. Next, we can discuss about the integrated rate equations. In that, first we can discuss about the zero order reactions. A reaction is said to be zero order means if the concentrations of the reactant molecule is independent upon the rate of the reactions. That means it is termed as a zero order reactions. So consider the reactions A to B. In this reaction, if it is zero order means we can express the rate equation as R is equal to K into concentration of A raised to 0. And when we look at examples of a zero order reactions, we have last session we have discussed the decompositions of ammonia by gold or platinum. Catalyzed by gold or platinum is an example of a zero order reactions. In that reactions, the rate is independent upon the concentrations of the ammonia. Similarly, we have discussed the photochemical combination of hydrogen and chlorine molecule resulting in the formations of HCl is also an example of a zero order reaction. That means the rate of that reaction is also independent upon the concentrations of hydrogen as well as the chlorine. Similarly, some enzyme catalyzed reactions can also be considered as a zero order reactions. So let us look how to write the integrated rate equation for a zero order reactions. So consider the reaction that is A to B, and if it is a zero order reaction means we can write the rate law as R is equal to K into concentration of A raised to 0. And any number raised to 0 according to the mathematical concept it is equal to 1. So we can write it as R is equal to K. So rate we have already discussed that it is a change in concentrations per unit time. So we can express the rate of this reaction as minus dA divided by dt. In terms of reactant we can write it as minus dA divided by dt is equal to K. So on rearranging, that is on cross multiplying, we can write it as d of concentration of A is equal to minus K dt. So then we can integrate on both sides, that is integrating dA, concentration of dA is equal to integrating, that is minus K dt. Again when we are integrating, that is 1 dA, that is changing interval is A. So 1 dA on integrating we are getting concentration of A is equal to again minus K is a constant, so we can put outside again 1 dt integrating we will get D. Plus again we are adding a constant of integration that is C. So to find the constant of integrations we are putting an assumption. That is assumption is that when initial time, that is when reaction is not starting means the time period we can start it as 0. Take it as 0. So when T is equal to 0 the concentrations of A can be taken as A0. So that is concentration of A can be put as A0, then we can find the C in substituting in this first equation we can get the C, value of C as C is equal to concentration of A0. Then after that we can substituting in the first equation we will get concentration of A is equal to minus KT plus concentration of A0. Then on rearranging we will get the rate constant or specific reaction rate as K is equal to concentration of A0 minus concentration of A divided by T. So this is the integrated rate equation of a zero order reactions. So we found that the integrated rate equation for a zero order reaction is, that is, concentration of A is equal to minus Kt plus concentration of A0. So next we can look the how we can plot graphically a zero order reactions. Again, when we look this integrated rate equations, it is in the form of y is equal to mx plus c. That is the general equation of a straight line. So again, when we are plotting a graph between concentration of A on the y-axis and time on the x-axis, we will get a straight line. With slope, we will get, that is, minus k. Because here x is t and y it is concentration of A. That is why we are plotting a graph between concentration of A on the y-axis and time on the x-axis. Then we will get a straight line, but we will get a slope of negative k and intercept as concentration of A0. Next, we can discuss the half-life of a reactions. Half-life of a reactions is denoted by T half. And this half-life means it is the time required to reduce the concentrations of the reactant half of its initial value is called as the half-life of a reactions. So, we have found the zero order reactions integrated rate equation as K is equal to concentration of A0 minus concentration of A divided by T. Again, when this is the time of the final concentrations, that is when T is equal to 0, that is when reaction start means T is equal to 0. At that time, the initial concentration is A0. So when T become T half, then this A become, that is final concentration, A become, that is A by 2. So in terms of this final concentration, we can write it as when T is equal to T half, that is A become A0 by 2. So on substituting in this equation, we can get, that is A is equal to K is equal to concentration of A0 minus concentration of A0 by 2 divided by T half. So we will get, that is A0 minus A0 by 2 means that is A0 by 2. So K is equal to A0 by 2 divided by T half. So T half for a zero order reaction will be, it is equal to A0 divided by 2K. So we found that for a zero order reactions, the half-life period is directly proportional to the initial concentrations of the reactant. Similarly, the T half is inversely proportional to the specific reaction rate, that is K. So for a zero order reactions, that is T half is getting as A0 divided by 2K and integrated rate equation is found to be, that is K is equal to concentration of A0 minus concentration of A divided by T. Next, we can discuss the integrated rate equation for a first order reactions. So, first order reactions, generally we can take an equation, that is a chemical reaction A to B. And if it is a first order reactions means we can write the rate equation as R is equal to K into concentration of A raised to 1. So, in a first order reactions means the rate is depending upon the any one of the concentrations of the reactant. That means it is a first order reactions. So again the rate is equal to written as K into concentration of A raised to 1. Here rate can be written as minus dA divided by dt is equal to K into concentration of A. Then rearranging, that is A concentration should become on the A side, that is dA side, and T on other side. So we will get, on rearranging, we will get, that is dA divided by concentration of A is equal to minus K dt. Then we have to integrate, and integration of dA divided by A is equal to integration of minus K dt. So 1 by A integration, that is 1 by A of dA, that is 1 by x dx means integrating, that is we are getting log x. So similarly dA divided by integrating, the divided by A integration means it is log A, that is ln A is equal to, again K, it is a constant, so we can put outside, it is minus K. Then 1 dt on integration we will get T plus we are putting the constant of integration. Again we are taking an assumptions to get the value of C, that is constant of integration. That is when reaction is not starting, that is when time period is equal to 0, then the concentration of A become, that is initial concentration, that is A become A0. Then putting on C, we will get, that is ln A is equal to in this equation, that is ln A is equal to minus Kt plus C, we are putting the value of the to get the value of C. So ln A0 is equal to C. So on substituting this value of C in first equation, we will get ln of A is equal to minus Kt plus ln of A0. So this is the rate equation for a first order reaction. Next, to convert the ln A to log A, we have to divide by 2.303. So we will get, that is, log of concentration of A is equal to minus Kt divided by 2.303 plus log of concentration of A0. Again, when we look this rate equation, it is also again in the form of y is equal to mx plus c. So when we are plotting a graph between log A on y-axis and t, that is time period, on the x-axis, we will get again a straight line with a negative slope, that is minus k divided by 2.303, and again intercept as log A0. So this is the rate equation for a first order reaction. So we have found the integrated rate equation for the first order reaction as, that is, log A is equal to minus Kt divided by 2.303 plus log A0. Again, on rearranging, we will get, that is, Kt divided by 2.303 is equal to log A0 minus log A. Again, log A, this is in the form of log A minus log B, that is log A by B. So we can rearrange as Kt divided by 2.303 is equal to log of A0 by A. So this is the integrated rate equation of a first order reaction. Again, on rearranging, we can write it as K is equal to 2.303 divided by T into log of A0 by A. Again, we have to find out the first half-life of the first order reactions. Half-life means it is the time required to reduce the concentrations of the reactant to half of its initial value is termed as a half-life. So again, for a first order reactions, when T is equal to T half, then the concentrations of A, that is final concentration, will be changed to A0 by 2. That is, it is reducing the initial concentration to half. Therefore, A becomes, this is the final concentration. So A is reduced to half, that is A0 by 2. So again, we can substitute in this equation, that is K into T become T half, to find that half-life of the first order reaction. So K into T half divided by 2.303 is equal to log of, again substituting A0 divided by A, here it is A0 by 2. So we will get, that is T half divided by 2.303 is equal to log 2. So on again rearranging, that is Kt half is equal to 2.303 into log 2. Again log 2 is equal to 0.3010, and again multiplying, we will get the value, that is 0.693. So Kt half is equal to 0.693. So T half is equal to 0.693 divided by K. So this is the half-life of the first order reactions. So when we look the half-life of the first order reactions, it is inversely proportional to the specific reaction rate or rate constant of the reactions. But in the first zero order reactions, we found that half-life is directly proportional to the initial concentrations of the reactant and inversely proportional to the specific reaction rate. Here, the first order reactions, that is T half, is independent of the initial concentrations of the reactant, but it is inversely proportional to the specific reaction rate or the rate constant of a reaction. So that is all in this session. Hope you like this session. Stay tuned for the next session. Till then, bye.